Hello ladies and gentlemen, and welcome back. Today's our second day of doing some proofs. We're jumping into some lines and angles, and you probably remember several problems similar to these up here where we had some either corresponding angles or same side interior angles, and we could set up equations that that allowed us to solve for a missing angle. Remember that corresponding angles are always congruent to each other, so these angles would be congruent to each other. Same side interiors, like these two angles, always added up to 180 together. And we're going to be using those postulates, those theorems, to prove several relationships with angles today. And I'm going to jump right into it. If you did not watch the first video on proofs, I strongly recommend jumping into that before moving on. We're still going to continue using the various reasons that we start out with last time, definition of supplementary and complementary, but we're going to jump in as well into some things like the alternate interior angle theorems, alternate exterior angle theorems, corresponding angle theorems, same side interior angle theorems, etc. that we started using in chapter 3. So let me go ahead and get rid of this document and begin. Now, if we're given that line R is parallel to line S. Line R is parallel to line S in this diagram. Well, right away we can say a lot of things. 1 and 2 are same side interiors. They have to add up to 180. 1 and 3 are correspondings. They have to be congruent to each other. Here's what I'd like to do, though. I want to prove that same side interior is actually a true statement without using same side interior theorem, because it's easy to say, well, 1 and 2 are same side interior, done. Right? It's easy to say that. I want to prove same side interior is a true thing. So just like last time, we're going to start our very first statement is always going to be our givens. Excuse me there. It's always going to be our givens. So step 1, I'm going to say that R is parallel to S, and we know that because that's given information. For number 2 now, well, what can we say looking at this diagram? I'm going to outline it for you, what we're going to say, and then we're going to say it in geometric speak. Basically, 2 and 3 need to add up to 180. They're a linear pair, right? 1 and 3 are correspondings to each other, so they need to be congruent. And then we're going to substitute 1 in for 3, essentially. All right? So let's go and write that out. Angle 1 is congruent to angle 3. We know that because they're correspondings. So I'm going to go and say that corresponding angles, and that's an S right there, angles, angle sign S. I can do better than that. Corresponding angles postulate. I need to start typing these things. Anyways, corresponding angles postulate tells us that. For number 3 here, I see that 2 and 3 are a linear pair. All right, 2 and 3 are a linear pair. So I can say that angle 2, measure of angle 2, plus the measure of angle 3 equals 180 degrees. I'm just going to type this out. And that's just definition of linear pair. So it fits. All right, that's just definition of a linear pair. The two angles that make a straight line together add up to 180. So now we're going to do some substitution. This last one is actually our very last step, number 4. I'm going to go and type this because my handwriting is awful here. Measure of angle 2 plus the measure of angle 1 equals 180. The reason we're able to do that is from this step, we know that 1 and 3 are congruent, so we're going to replace angle 3 with angle 1, doing some substitution. All right, so 4 I'm going to say we're doing substitution, and I'm going to note that we're using theorem 2 and step 2 and step 3 to do our substitution there, and say that angle 2 plus angle 1 is equal to 180, which is exactly what we wanted to say. So we're done with our proof. We were able to lay out a few steps, and we've proven that same side interior angle theorem is actually a true statement. Moving on here, let's look at one other proof. I'd like to give a shot at this one towards the bottom. Suppose that L and M are parallel to each other. And we also know that 1 and 3 are congruent angles. I want to prove that P and R are also parallel to one another. All right. So that's my goal. I want to prove that those are also congruent, or also parallel to one another. So, like always, first step, what do? We go ahead and write out our givens. So step number 1, L is parallel. You know what? I can actually make straight lines. Well, look at that. L is parallel to M, and we know that. And we also know that angle 1 is congruent to angle 3. We know that because it's given information. All right. For step number 2, now I'm going to explain this to you real quick here, what's going on. I'm going to say that 1 and 2 are congruent because they're corresponding angles, and we have parallel lines. All right. I'm then going to say that 2 and 3 have to be congruent because 1 and 3 are congruent. That's called transitive property. If 1 and 3 are congruent and 1 and 2 are congruent, 2 and 3 have to be congruent. It's called transitive property of congruence. And then since 2 and 3 are congruent and alternate exteriors, we can conclude that these two lines, the P and the R lines, are going to be parallel to each other. That's going to be our last step. So let's go ahead and do that. Angle 1 is congruent to angle 2. Again, how do we know that? We know that because they are corresponding angles, corresponding angle postulate. Corresponding angle postulate, or theorem, I think it actually is. Corresponding angle theorem. Number 3, we can go ahead and say angle 2 is congruent to angle 3. And we can say that we're doing some substitution here now. 1 is congruent to 3, so I'm going to replace 1 with a 3, then 2 is congruent to 3. So we're doing transitive property of congruence, or you can just go and write substitution. Using steps 1 and 2. And then as our last step here, I'm going to go ahead and state what we actually wanted to prove, that R is parallel to P. All right. How do I know that R is parallel to P? Well, 2 and 3 are alternate exterior angles in this set where we have two parallel lines being cut by a transversal. All right. So 2 and 3 are alternate exteriors. Since they're congruent to each other, they've got to be parallel by the alternate exterior theorem. Now I want to make one note quick here. We did go ahead and prove, we have a solid proof right here. This alternate exterior angle theorem, we actually need to add something to it. If we're going to go forward in that direction, say two parallel lines, alternate exteriors are congruent, that's called the alternate exterior angle theorem. If we're going to go backwards and say we have alternate exterior angles that are congruent, therefore lines are parallel, we're going to go backwards. This is actually called the converse of the alternate exterior angle theorem. But essentially they're doing the same things backwards and frontwards. Converse just means we're going in reverse. All right. So again, we're going in reverse. Rather than saying two parallel lines imply these are congruent, we're saying these two being congruent imply we have parallel lines. If you have any questions about today's presentation here, definitely shoot me an email. Let me know. I'd love to chat with you about some proofs. Otherwise, assignment is on Moodle. You have a terrific day. Take care.